Welcome everyone to day 3 of this fantastic conference. I hope you've all been enjoying it. The current session will be all online, so maybe some of you would have preferred to stay in your rooms the whole morning, but they told me I had to show up in person, so I'm glad you did too. Our first speaker of the morning is Sen Peng Eu from the National Taiwan Normal University. He'll be giving us an invited 15-minute talk on sign statistics on permutations. Please go ahead.
Okay, thanks for the introduction and thanks for the organizers for the invitation. And today I would like to share with you the sign statistics on permutations from symmetric group to Coxeter groups. I'm Sen Peng Eu from National Taiwan University. The outline of this talk is that we'll give an overview of the framework and then introduction of some selected results in the 4 topics. The first is alternating permutations, snakes, and Euler identity. The second will be the Arnold families, Simsun, and the Andre permutations. And the third will be the signed Mahonian and signed Euler Mahonian identities. And the fourth will be the signed counting over restricted subword. Then, after a very sketchy description on methods of proof, I will share with you some remarks and ideas. And let me here to thank all my co-authors. And a permutation statistic is a function, just a function from the symmetry group to the non-negative integers. So why do we start it? Well, you can say that permutation is a fundamental structure, and that's the reason. But for me, well, that's for fun. And this is a very classic topic, so maybe it's somewhat a bit dated, but we believe that it is still worth to be mentioned. So over the symmetry group, there are 3 fundamental families of statistics, Mahonian, Eulerian, and Stirling. Let me briefly introduce them one by one. And Mahonian statistics, first we have inversion, which counts the number of pairs big small if reads the permutation from left to right. Yeah. Then we have a measure which counts the sum of indexes where the values decreases. And a classical theorem of McMahon says that inversion and measure are equally distributed over the symmetry group. So we say a statistic is Mahonian if it is equally distributed with the inf. Then we have Eulerian statistics, first studied by Euler, the descent statistics, which count the number of places, there's a decrease. Then we have exceedance, which counts the number of places where the values are too big, bigger than the indexes. Then by the fundamental transformation of photon, you can prove that these two are equally distributed over the symmetry group. So we say a statistic is Eulerian if it is equally distributed with this two. The third family is the Stirling statistics. We have a cycle which count the number of cycles in the cycle notation. Then we have LR mean left to right minima, which counts the number of local minimas from left to right. And again, by the fundamental transformation of photon, you can prove that these two are equally distributed over symmetry group. Because the cycle counting is by the Stirling number of first kind, so we say that a statistic is Stirling if it is equally distributed with a cycle. Okay, now the point is that the symmetry group can be seen as a Coxeter group or a reflection group, depending on what's your viewpoint. And we know that there's a full classification of finite Coxeter groups type A, type B, type D, and a bunch of exceptional types. And the symmetry group is exactly the type A. Or you can see it as a complex reflection groups, GRPN. And in this case, symmetry group is G11N, and type B is G21N, and type D is G22N. So it is natural to extend the result in symmetry group to these groups. Also, some statistics have unified definitions over the Coxeter groups. For example, the inf. In Coxeter group, there's a concept called the length. Length is the minimum number of generators needed to get the element. So in Coxeter group, we define the length to be the inversion statistic because in type A, the value of inf exactly is the same with the value of length. Also, the descent in Coxeter group, we have a unified definition of descent. We define descent is a cardinality of the descent set, which collects those generators by apply them to the elements, the length will decrease. Unfortunately or fortunately, for other statistics, there are no unified definitions. This makes the generalization interesting. And we have permutation models for type B, type D, and GR1N. For type B, the permutation models are the side permutations. You take ordinary permutation and you can put negative signs on any letters. Then for type D, the negative letters, number of negative letters should be even. These are even side permutations, and these are the models of the type D Coxeter group. And the generating function for the type B and type D for the length generating functions are nice, very nice. But even so, if you want to read the length from the permutation model, this is not so easy. Yeah, there's some delicate formula here. And for the GR1N, the permutation model is the R-colored permutations. You take a permutations of length n, and for each letter, you can color it in R colors. These are the color permutations and the combinatorial model for GR1N. But note that the generating function for the length is not R to R, 3R to NR. Okay, so based on these reasons, well, the direct generalization of the results in type A, well, sometimes it is not so trivial. So the framework is this. In the past 10 or 20 years, it is a paradigm to find the Coxeter version for classical results in combinatorics, and it was successful, very successful in some topics. For example, the Catalan combinatorics or the parking function and so on. So in permutations, the framework will look like this. You can take the Sn to Bn to Dn this road, or Sn to Bn to Gr1n this road. So in the following, we will introduce some of them, all selected from some our recent or not recent work. The first topic is alternating permutations, snakes and Euler. This is a bit old, but I like this result, published in Advanced Applied Math. So an alternating permutation has a shape, zigzag shape, and they are counted by the Euler numbers, 1, 1, 1, 2, 5, 16, and so on. Back then, 250 years ago, Euler proved that the exceedance balance over the symmetry group result in the Euler number if n is odd. Then, after about 100 years later, Roselle completes the other half. He proves that exceedance balance over the fixed point free permutations, yeah, which means derangement, results in the Euler numbers up to a sign if n is even. So combine these two, we have a full picture. And these identities have a Q analog. It is done by Joshua Verger in 2010. Now, exceedance is replaced by the weak exceedance, and the Q counts the crossing number, which is the number of crossings if you draw the permutation in some certain way. And the result is a Q Euler numbers. Yeah, depends on the n is even or odd. We have a two set of identities. And the Q Euler number is defined by Han and Rajana Rivani and Zen in the form of continued fraction. So these are the background, and our goal is try to generalize these identities. So first of all, we need the concept of Euler number in other types. These are called the Springer numbers. And for Coxeter group, we take a subset of generators and look at those elements whose descent set is what we select, the J. Then the Springer number of W of the Coxeter group is the cardinality of the largest descent classes. And it happens that in type A, the largest set are exactly from the alternating permutations. So the type A Springer numbers are the Euler numbers. And for the type B and type D, we can also compute them. The type B Springer numbers are 1, 3, 11, 57, and so on. And type D are 1, 5, 23. Let's just memorize them for a while. It will be useful. The second is that we need the concept of alternating permutations in other types. These are called snakes. So let's define three kinds of snakes on the signed permutation. The Sn snakes has the zigzag shape. Then Sn0, yeah, we put another condition, the sigma 1 is positive. Then Sn00, we put another condition if the tail swings to the correct side. Now the Arnold and Joshua Verger proves that they have a nice counting. The Sn0 is counted by the type B Springer numbers, and the difference of Sn and Sn0 is counted by the type D Springer numbers, and the other two snakes is counted by the Euler number times power of 2. So that means Springer numbers have combinatorial models in snakes. So the last piece we need is to find a good statistics. It turned out that correct statistics for sign is the flag weak exceedance, which defined as this. And in fact, we are counting the balance of half of flag weak exceedance. So this is our result over the type B or type D permutations. If we count the balance of half of flag weak exceedance, then we got the number which counts as Sn snakes. Okay. If we count over the fixed point free type B or type B permutations, then we got the Springer number of type B. If we counted on the difference of Bn minus the Bn star, then we got the type B or type D Springer numbers, depends on the parity of n. So this is our main results, but we can do more. We can have a Qt analog. In this case, T counts the number of negative entries, negative letters, and Q counts the crossing number, type B crossing number, and the balance result in the polynomial in T and Q. We call it R, T and Q, if we count over the type B permutations. Or if we count over the type D permutations, we have a similar result. Or if we count over the fixed point 3 type B permutations, then we got another polynomial which called QNTQ. Or if we count over the type D fixed point 3 permutations, we got another set of identity. And crossing, type B crossing and the QR polynomial. Just a brief introduction. The type B crossing number is defined by Coxeter, Chauvet, and equivalence, which is a generalization of type A crossing numbers, yeah, in some certain way. And Q and R polynomial can be defined from some operators, and a theorem of Chauvet states that the generating function of Q and R can be written in the form of a continued fraction. So this is end of the first topic, and I'm happy with this result because you know that there's not so many chances to generalize Euler's results directly, right? So that's the first topic. Then the second topic is about the Arnold family, Sen Simsun,
Sorry,
and
can I ask a question?
okay.
Sen Peng? Could you go back to the crossing number definition? I just, you went too fast. Oh, for type A, sorry. I was wondering if, is it one of the Eulerian or Mahonian statistic? I just didn't follow the definition
No,
of.
crossing is not Eulerian or Mahonian or anything. Yeah.
Okay, okay.
Okay.
So it's, you just draw the.
Yeah. I just draw the permutation in some certain way and count the crossing. Yeah.
Okay,
Okay.
okay, thanks.
Okay. Now the second topic. Well, where is? Okay, here. The Arnold family seems only under permutation. This part will be proved later in Arnold Mathematical Journal. And now we know that in terms of alternating permutation, the snakes, we have an interpretation of the Springer numbers. But in type A, they are the Euler numbers. But there are other important permutation families counted by Euler numbers. For example, the Simsun permutations and Andre permutations. But most of their type B counterparts are missing. Yeah, so our goal is to fill the blanks. We need a checkpoint. This checkpoint is called integer numbers. The Euler number can be generated by Boustroff-Fedon triangle. Yeah, it will work like this way. We put a 1 here. Can you see the hand here? Yes, okay. Then we put 0 here, and 0 plus 1, we got 1. Then we put 0 here, and 0 plus 1, we got 1. And 0 and 1 plus 0, we got 1. And put 0 here, and again we got 1, 2, 2. Then put 0 here, we got 2, 4, 5, 5, and so on. So these are called integer numbers, and the integer proves that they are exactly the number of alternating permutations of length n by the leading numbers. For example, the 0, 1, 2, 2 here is the number of alternating permutations of length 4, lead by 1, yes, no, and lead by 2, 3, and 4. So we have 0, 1, 2, 2. These are called integer numbers. Then we have Arnold numbers. Arnold extended Boustroff-Fedon algorithm to 2 triangles. We put 2, 1 here and do the same. But whenever we got a number at this edge, then we copy it to the other edge. Okay. And 1, 1, 2, and put 0, 1. We have 2 and 3, and copy the 3 here, and we got 4, 4, and then we got 11, copy 11 here, and we got 11, 14, and so on. So we have this table. The point is that the sum of each row will be the snake, the number of snake Sn, okay? And the sum of those entries with positive k will be the type B Springer number. and the sum of those with minus n minus index k will be the type D Springer numbers. So we call this number the Arnold numbers V and K. And Arnold and Joshua-Verger proves that these numbers just count the snakes or type B snakes or type B snakes according to the first element. So this is good. So this is our checkpoint if you want to define a reasonable Simsun or under permutations. So this as a result, we have assigned Simsun permutation of the first kind. Let us recall what is called a Simsun permutations. A Simsun permutation is that for given k, for any k, fixed k, there's no double descent when you restrict the permutation to k, 1 to k. So this is not Simsun 3, 5, 4, 2, 1, 4, because if you choose k3, then we have 3, 2, 1. There is a double descent. But 2, 5, 1, 3, 4 is Simsun because for any k, well, you cannot find the double descent. So our result is that we can define signed Simsun permutation to be those signed permutation if the absolute value is Simsun. And if we put one more condition, we can define it as the type B Simsun permutation. And if we put yet one more condition, then we can define a type D. And the good thing is that the cardinality is correct and our checkpoint meets. If counted by the last entry, we result in Arnold triangle. So this seems to be a good definition of type B Simsun permutation. But we call it first kind because we find another set of Simsun permutation also seems reasonable. We call them the second kind. Now the signs Simsun permutation are those when restricted to minus k to k has no double descent. And after we put in some other conditions, then we can define them as a type B or type D. Again, the cardinalities are good, and by some nature statistics, we have entries in Arnold triangles. And we found that these two sets of definition both seems to be reasonable, so we call them the first kind, second kind. Okay, but we can do more. Yeah. Hoffman studied polynomials, Pn and Qn, two families of polynomials defined by continuous differentiates the tangent or secant function and derive their generating function like this. And we can prove that we can refine each entry of Arnold triangles into polynomial such that the sum of positive index of k will be the q polynomial, and the negative parts, the sum of them, will be the p minus q. This is good because you know if you recall the Arnold triangle, the sum of the left-hand side will be the type D Simsun Springer numbers. Okay, so these are the first few values of V and K, and now this is our final result. All the following, in fact, we have signed Simsun permutation of first kind and second kind and type B and type D. And also we have signed underlay permutations of the first kind and second kind and their type B and type D. All these 12 families can be refined to Arnold-Hoffman polynomials by some nature statistics. So this is our second topic. So, but well, there's some problems remains that because you know the Simsun permutation originally are from some connection with the geometry. So, so the next step will be to see that if there's any geometric interpretation or connection. Okay. as well as the Andrew permutation of both kinds. So the third part I would like to share is the signed Mahonian and signed Eulerian, signed Euler Mahonian identities. Sorry, and this consists of two papers, both published last year. One in Journal of Algebraic Combinatorics, the others from European Journal of Combinatorics. And the whole thing started from a fantastic identity of Gassel-Simeon in 1992. They proved that the signed Mahonian, now the sign is controlled by the inf, and the Mahonian statistic we take the major, the signed Mahonian polynomial, over the symmetric group will result in a very beautiful form. The product of Q and log, but whenever you have an even number, you plug a minus Q instead of Q into the Q and log. Then Ardeen, Guest, and Reutemann considered type B case. And for the sign, they consider all the one-dimensional characters of type B. So there are four of them, and this one is trivial, so they consider all three other signs to be the sign Mahonian. And for the major, they consider the F major, flag major, which is important, flag major. Then they come up with the signed Mahonian identity for three cases. All have nice form. Okay. Oh no. Then for the signed Mahonian, for the colored permutations, in colored permutations there are two R dimensional characters, and Caselli proves that they can be written in this way, indexed by epsilon and k. Epsilon will be minus or plus 1, and k is from 0 to up minus 1. And again, in the colored permutations, there is a direct generalization of F major, and we call it the F major of color permutations. Then Biaggioli and Casali prove that they can have a signed Mahonian identity in this sense over the color permutations, and take the sign to be all characters, each characters, and Mahonian statistics F major. They come up with a nice identity. Okay. What do we do? First, we can write the characters, 2R characters, into another form. Now they are indexed by A from 0 or 1 and B from 0 to R minus 1. And we take another major rather than F major. We take L major. The reason is that L major is equidistributed with the length function in the color permutations, and Bagnall proves that they are equidistributed and with a generating function like this. So we give the sign Mahonian identity in this sense. We take Mahonian statistics to be the length or L major, and we consider all the possible one-dimensional dimensional characters, and we come up with a result identity in closed form. And also for type B, and the only non-trivial one-dimensional character is this guy. So we consider the sign Mahonian identity also in type D, and we also have a closed form. But we can do better. And as said in the introduction part, except for inf and descent, for other statistics, we have no unified definitions in Coxeter groups. So from many contexts, you can have reasonable definitions for other statistics. So there are other reasonable Mahonian statistics on color permutations. For example, the following four are all equal distributed. F major, we have seen that. Then we have R major, we have F math, we have R inf. All different defined from a different set of all different people. Yeah, so we can consider this form. Yeah, over the color permutation, we take one statistics to be the sign and take the second counted by Q, and our result is that all have nice identities, closed form, except for two. Yeah, these two we cannot find the closed form, but for others, we all have nice identities. Now we turn to Euler Mahonian. Euler has a generating function of Dyson in this way, and Curtis considers its Q analog, then come up with a numerator like this. And this is a joint distribution of Dyson measure, and now it's called Euler-Mahonian distribution. And for the type A case, back in 1992, Desamelian and Folta proved this identity. I think the point, the spirit is that it connected the left-hand side is the side counting over the structure S2n, a side counting, and the right-hand side is a normal counting. It's the normal counting. So Folta and Desamania prove these identities, and then Vox proved a side Euler-Mahonian identity. Look like this: the side Euler-Mahonian identities over the S2n, and we result in a normal counting sine Mahonian, Euler-Mahonian, normal counting over the Sn, yeah, times a function. And for the type B case, Bajoli give a sine Mahonian identity, yeah, in the same form. And we have, what we do is that we gave it sine Euler-Mahonian identity. It looked like this. The left-hand side is a sine Euler-Mahonian identity over the side permutation of length 2n. The right-hand side is the normal counting of sine Mahonian over the Bn times a function. And we can mimic the idea of Ardeen, Rothman, and Gessel. We put all the characters of type B in, and it turns out almost all we have identity. We have a close identity linking the side version and the normal version. Yeah, it would look like this. Okay, but there are some delicate point here. If you look closely, I'll omit that. Yeah, for example, this one. Well, the left-hand side Dyson and the right-hand side Dyson, they are different Dyson. Yeah, it's curious. Yeah, in a sense, but that's a very delicate point. Then for the type D, we also have the identity of the same form, or similar form, I think. Yeah. And for the colored permutations, we have 3/3 of them. And except for the last line, the case GR1 2n plus 1 with the character indexed by chi1b, yeah, except for this case, we have a closed form as the theorem box shows. But for the last line, this case, just open, no conjecture yet. So this is a missing piece. So this is the end of the third topic. Yeah, I will proceed to the next one. So the side counting over the restrict subwords. Yeah, this consists of two papers. The first is from JCTA 2 years ago, and the next one is Advanced Implied Maths, published this year. And recall that the symmetric group can be generated by a bunch of generators where the SI is the adjacent transposition. Now we take the last K generators and we consider the parabolic subgroup generated by J. Then we consider the left parabolic quotient JW Yeah, JW will be look like this. Yeah, it's nothing but a collection of those permutations which the largest k values will appear in this order if you read the permutation from left to right. That's all. And we denote it by a superscript n minus k plus 1 and n and bracket. And Humphrey proves that the inversion generating function over this set has a nice form. It's just a tail of the Q analog product Q analog of last k, last n minus k plus 1 numbers. Then the Stanley Forta and the Schuster-Berger, yeah, says that even in this set, the inf statistics and the major statistics are equal distributed. Then Caselli considered the sign, the Mahonian counting over this set, and he come up with a nice closed form will look like this. You can see that it's quite delicate. For example, the k plus 1, you should plug in minus 1, epsilon is minus 1, to the power of nk plus n plus k well into it. So this is quite delicate. Okay, now we take the first generators. Remember that in the last few slides, we take J as the last generator. Now we take the first k generators. Again, we can consider the left parabolic quotient. Then JW will look like this. It is a collection of those permutations. The first k numbers will appear in this order, and look at the sign Mahonian over this set of permutations. And this is our motivation, which comes from a conjecture of Caselli. He conjectures that if n is even or k is odd, then over these two sets, indexed by 1k and indexed by n minus k plus 1 to n, over these two sets of permutations, the sign Mahonian will be the same. So our goal is to develop a general theorem to explain this. So here is our result. We call it R versus R plus 2 theorem. Let R be a partial order among the numbers from 1 to n minus 2, and R plus 2 be the partial order among 3 to n by an increment of 2. Yeah, and Sn R superscript R collect those permutations whose index is consistent with all the relations in R. Yeah, let me give an example. Yeah, for example, if we took n is 5 and R, the relations like this, partial order 1 less than 3 and 2 less than 3, then R plus 2, yeah, is 3 less than 5 and 4 less than 5, just increment by 2. Then S and R are those permutations in which 1 and 2 appear before 3. And S and R plus 2 are those permutations in which 3 and 4 appear before 5. So this is our main result. For an arbitrary partial order on n minus 2, we have the equality between the two sets of permutations. We count the side Euler Mahonian, then the left hand side is over the SNR, the right hand side is over SNR plus 2. So this is the result. So now we can give an explanation, interpretation, or reason why the Castelli's observation is true. Yeah, let us say that Sn1k, the sign Mahonian, is indexed by 1k. So because the R equivalent to R plus 2 theorem before, we know that the sign Mahonian polynomial indexed by 1k will be the same with the 3k plus 2. will be the same with that indexed by 5, k plus 4, and so on. And again, the index by 2, k plus 1 will be the same with that indexed by 4, k plus 3, and so on. And we can prove that if k is even, these two polynomials are different. So that explains why n is odd and k is 0 fails, because when k is even, these two belongs to different families, because from this one there is impossible to shift to become this one. Yeah, for k is odd. Now for k is odd, the situation is better. Yeah, even we increment by 1, they are of the same. So when k is odd, all shifts are of the same. So this explains the Coxeter's observation and confirm his conjecture. And the R versus R plus 2 theorem has some interesting applications. Yeah, we point out two here. The first one is a linear extension of an arbitrary pole set. Let P a pole set and let F be an injective labeling from P to n minus 2. And again, F plus 2 be the labeling by an increment of 2. So we consider the linear extension of both two labelings. The same pole set but two different labelings. So we have two sets of linear extensions. So the theorem says that for any partial order and any injective labeling, the sign, the Euler Mahonian over the first set of permutation will be the same with the second set of permutations. So this is our first applications. And the second application is about pattern avoidance. Now we know that given pattern pi and a subset from 1 to n minus 2, and then we have s plus 2 is a subset from 3 to n. Now we define the AV and S pi, the avoidance, collect those permutations. The pi avoidance are only for the values in S. And AVSN plus 2 are those permutations. The pi avoidance are only for values in S plus 2. Okay, again, this is for a single pattern pi, and for set of patterns, we define AV and SP and AV and S plus 2P similarly. The result is that let's P an arbitrary set of patterns and S be a subset from n minus 2. Then over these two sets of permutations, the AV and SP and AV and S plus 2P, the sign Euler Mahonian counting are of the same. So, and for other types, the type B and type D and quarter permutations, yeah, I will only briefly mention this. The above on the restricted words can be extended to other types. And moreover, we can put all characters, the parity, the word restrictions, all these concepts into place. For example, yeah, if B and N are of the same parity, depends on N and K are of the same parity or not, we can have a signed Mahonian identity where the sign is the character, and Mahonian we take F major, and over the restricted words on the color permutations. Yeah, there are many theorems in this form. Yeah, so I omit it. So about the proof, I will say something, in fact nothing about the proof. Yeah, the proof in fact use very different techniques for each paper. And for the snakes, mainly we use continued fraction and lattice path model. And for the Arnold families, mainly we heavily use the tree structure from Jules and some bijection techniques. And for the signed Euler Mahonian or signed Mahonian, we use combinatorial arguments, the cancellation. And for the parabolic subgroup and words, for type A, yeah, we proceed by purely bijective approach. But for type B, D, and the correct permutations, it seems that pure bijective approach is very, very difficult. And so we use generating function plus some combinatorial arguments. Yeah, this is all I can say about the proof. I'm sorry. And the last few minutes, I will try to share some remarks and ideas which I find them interesting. The first is called the folding phenomenon. And during the exploration, the following pattern emerges over and over. And let us call it the folding phenomenon. Yeah, basically, you take a structure of size 2n, then you do the sign counting. Yeah, you pick one statistic for the sign and pick another statistic for the q. Then you got the normal counting, yeah, with respect to the second statistics. But now the counting will be doubled. And also the ground set will be the size n. And the result times a function, usually a rational function. For example, box identity, yeah, it's a typical. Yeah, over the signed permutation of type B of length 2n, you do the signed counting, signed Mahonian counting, then you got the normal counting over Bn, but now the F major should be doubled, and the result with times a rational function. It's interesting that, in fact, we have more than 30 examples in this form. Yeah, we don't know why. Yeah, and not only over permutations, we have example in trees, in Catalan structures, and in tuple, in partitions. Yeah, so I don't know why this pattern emerges. Not so frequently, but frequently. Yeah. So my question is that is there anything lurking behind or just a bunch of coincidences? Okay, this is the first comment. And the second idea I would like to share is the relative statistics. We can define the relative inversion of sigma with respect to pi. Yeah, this extends the k-relative inversion of Gillespie and Kaliswski and Morse. And for the relative inversion, yeah, well, simply put, you just if you want to count the relative inversion of 132 with respect to 231, you just put 231 at the top and 132 at the bottom, and try to find a triangle in this way. And along this direction, yeah, the order follows. That's all. So in this case with 3, 3, 2, or in this case with 3, 2, 1. Okay. Okay. So if it satisfied one of these three inequalities, then we say we have a pi inversion. Okay, so the relative inversion of 132 with respect to 231 is 2. So now we can compute the relative inversion of each permutation with respect to other permutation. So this is a S3 case. So we have 6 new statistics, but if you look at closely, this column and this column, the relative inversion with respect to 1, 2, 3 and 1, 3, 2, well, they seems to be symmetric. We have 3, 2 here, and then we have 2, 3. Yeah, we have 1, 0, then we have 0, 1. But if you look at this column, these two columns, these are not symmetric. We have 2, 1, but we have, oh no, we have 2, 1, we have 1, 2. We have 3, 2, but we don't have a 2, 3. So these two are not symmetric. Our result says that inversion pi1, inversion pi2 is joint symmetric over symmetric group if there's an edge connecting these two permutations in the weak Buchholder. And moreover, we can define the relative descent, relative measure, etc., and all inherit nice properties. But the question is that this is not if and only if. That means there are some symmetric case, but the permutation are not connected by an edge in the weak Boole order. So the question is that if we can complete only if direction and generalize other types. Okay, the last one is the partial permutations. A partial permutation is a square 0, 1 matrix with some 0 rows or columns. And let P and K be the size n by n and with K 0 rows. It's easy to count the number of them. It will look like this. When K is 0, there's no 0 row. Well, we have an ordinary permutation. Simply put, a partial permutation is take a permutation matrix and delete some ones. And the point is that we can extend almost all classic statistics from ordinary permutation to partial permutation. For example, the inf and the Arion mean. You delete all the entry to the right and below of each one and count the remaining zeros, yeah, with certain restrictions. Then you got a result like this. Yeah, it's apparently a generalization of sturdy number first kind and the Q sturdy number first kind. And moreover, the P and K, the matrix, counting matrix, can be realized as Coxeter matrix, which can be defined from two seeds and a recurrence relation. And it turns out the many results can be coded in seeds. Yeah. Yeah, for example, the previous example, if we take C to be like this, then the Coxeter matrix produced entry is exactly the general function with respect to Arion mean and weak exceedance inversion. I found this idea that everything is encoded in seeds. I found it quite interesting. And my question is that if we can extend this to type BD or other structures. And the last slide, more on side counting. In combinatorics, there are many nice theories involving side counting, the determinants, the hyperplane arrangement, the cyclic orientations, Ehrhart polynomials, and reciprocity, Möbius function, cyclic sieving or -1 phenomenon. That even pertaining to permutations here, there are still many missing pieces. So the question is that if we can fulfill the missing pieces and explore more, we believe that although this topic is classic, ancient, has a story, but we believe that there are much to be done. So permutation, my conclusion is that permutation statistics still have a lot of fun. Thank you very much. Thank you.
Are there any questions? Please raise your hand and somebody will bring you a mic. Hi, that was an amazing talk. Thank you. You mentioned towards the end of your talk the Catalan matrix, and you asked if there's some sort of type Bn analog for these things. I mean, I don't know if that's the question, but I just want to ask you if there is, do we understand a theory of orthogonal polynomials? Is there an analog of that for type Bn somehow? Is there a way of, is there a different theory? If the classical theory of orthogonal polynomials, the type An theory, is there something which could be considered a Bn analog of that?
You mean the Catalan matrix or the parabolic part? I'm not so sure about your question.
No, all I'm saying is that many of the type An identities, as you mentioned,
are coming from this setting of orthogonal polynomials.
Yes,
Right?
yes.
So is there something analogous to that which would give type Bn identities?
I think so, but I didn't try it yet. Yeah, I think it's possible to do that. Yes, yes, but I didn't try it yet seriously. Sorry for that. Yeah, but I think it's possible. Okay,
Okay, I'll email you maybe. Yeah.
okay, okay.
Oh, yeah. The folding phenomena that you showed us that reminds me of the Cambridge's Q equals -1 phenomena. Do you think there is any connection between them?
Yes, I think so, but you know, I still cannot find a connection, a really deep connection of them. But in fact, it bugs me because the folding phenomenon, as I mentioned, we have more than 30, in fact, more than 50 uh, identities in this form. But it seems to me so far that all these identities are independent. I mean, there's no relation between them, so I cannot see if there's something. Yeah, maybe they are just a tip of some iceberg, or maybe they are just coincidence. I don't know. I really don't know. But thank you for the question.
You mentioned these generalized inversions, inversion with respect to pi, relative inversions, you call them, right?
Yes.
So if I fix some pi, let's say of size 3, like 132 or something,
Yes.
do you have a nice formula for the number of or the generating function q to the inv 132 of pi for any pi for sigma in Sn?
Okay, that's a very good question. As we can see that, okay, they are here. Here it is.
Just a minute, it has not started sharing yet. I mean, it's
Yes.
not sharing yet.
Okay. As you can see that fixed
Okay.
inversion, then we have a relative inversion, right? And
Yes.
yes, and if there is a good generation function, some of them we have.
Yes.
Yeah, yeah, some of them we have. But if you want to consider the joint symmetric version, if we have a Qt bivariate generating function, then I must say the situation is very complicated. Yeah, for the n is 4, yeah, we have 12. No, we have 24. We have 24 relative inversions. So we have 576 pairs of joint symmetric version,
Yes.
and they can be classified into I think 14 or 6. I forgot. Yeah, they can be classified into several families. Some of them we can find the generate function, but some of them are still missing. Okay, this is all I
So
can.
they're of nice product form. I just
No,
this the nice ones. Okay.
no,
Okay.
no.
Okay. I see.
Okay.
Okay. Thank you.
So I have a question. So some of these you count things, but can you refine by considering like set value statistics instead? Like instead of just looking at the number of descents, you can keep track of the set of descents, say.
Oh yes, 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 yes. In fact, some of the paper I mentioned, we in fact have the set value version of the theorem, but I didn't show it. Yeah, because I think it will be too complicated. Okay, thank you.
Thanks.
So I have rather a comment. So if you are looking for symmetric joint distributions, I would like to advertise Feinstadt. For example, there was a talk about Stirling statistics. And then the question arose whether there is a joint distribution for Euler, Mahonian, Stirling statistics. And it takes about 5 minutes to code something to come up with such a pair, or actually a few pairs, triples, pairs of triples of statistics. So we also have this for sign permutations. For permutations, we have currently roughly 400 statistics in the database. For sign permutations, we only have something like 20. And it would be very nice to get this up to, say, 200 or 800. I don't know, depending on the sign. Many thanks. Sorry.
Yeah. Hi. So I wanted to ask if there are other type analogs for the Genoki numbers. I remember because you mentioned the Boustroff-Udron array and things. So I was wondering if there are other
Yes,
type.
yeah, very good question. We are doing that now. Genoki numbers of type B. Yes.
Thank you.
Okay. Well, let's thank the speaker again.
Thank you very much, and thank you,
Oh.
Arvind. Yeah, thank you, Tom.
Thanks, Sen Peng.